Neil deGrasse Tyson once said, "The universe is not only bigger than we can imagine, under most scales, it is bigger than we can imagine." This profound observation invites us to ponder some of the most fundamental questions in cosmology. Does the universe have an end and a beginning? Has the James Webb Space Telescope, JWST, finally uncovered the edge of the observable universe? Since the dawn of human civilization, we have strived to comprehend the vastness of our world. Our quest to understand its boundaries and truths has continually expanded our knowledge. In the past, the edge of the world was thought to lie just beyond the horizon. Today, we use sophisticated telescopes to probe the universe, searching for clues about whether our universe is finite. With the advent of the JWST, we may be on the verge of achieving a breakthrough in this fundamental question. The concept of an edge in the universe is not straightforward. An edge might not signify the end of the universe but could represent a threshold leading to another universe or unknown dimensions. While Earth, our solar system, and the galaxy have edges, the cosmos itself does not end there. As Neil deGrasse Tyson aptly put it, the problem with the size of the universe is in our heads, and not in the universe itself. The universe is indeed larger than our imagination can fully grasp. Our tools for exploring it are still comparatively modest. Currently, we are able to observe about 46.5 billion light-years in every direction, giving us a total observable diameter of approximately 93 billion light-years. Despite this immense scale, we have yet to find an end. The mass of stars, galaxies, and phenomena within this observable universe is beyond imagination. It would take us thousands of years to explore every corner of the universe that we know so far. Yet, driven by insatiable curiosity, we continue to search further and further. The JWST has played a crucial role in this endeavor, potentially illuminating whether the universe has an edge and what it might look like. Neil deGrasse Tyson's observation on the JWST is telling. The James Webb Space Telescope identifies objects in the darkness that, according to the best measurements we have, are large, fully developed galaxies. Humans tend to think in terms of beginnings and ends, often visualizing structures as spatially limited and confined. However, dealing with the universe challenges these perceptions. To grasp the vast dimensions of the cosmos, we must stretch the limits of our imagination and perception. The JWST has revealed 6 galaxies that are so old and perfectly developed that they seemingly defy expectations. Initially, the telescope was designed to look into the so-called dark ages of the universe, a period when the first stars and galaxies were forming. However, instead of detecting protostars and nascent galaxies, the JWST has uncovered mature, well-developed galaxies. This finding raises intriguing questions. Are we truly observing the universe's beginning? Did the dark ages as we conceptualize them actually exist, or have we misinterpreted this phase because of our limited understanding? In addition to these ancient galaxies, the JWST has discovered a massive cluster of galaxies that appears to have existed far too early in the universe's history to be possible. Until now, the prevailing theory suggested that individual stars formed first, followed by star clusters, galaxies, and then galaxy groups. The existence of such a galaxy cluster at a time when the universe was still young challenges these assumptions and prompts us to reconsider our understanding of cosmic evolution. The JWST's revelations about galaxies with a redshift greater than 10 are equally astonishing. A redshift greater than 10 implies that these galaxies existed when the universe was only about 2% of its current age, just a few 100,000 years after the Big Bang. These discoveries challenge our perception of the universe's early state, suggesting it might have looked much like it does today, contrary to previous assumptions. The sheer magnitude of these findings initially led to skepticism among scientists. However, the JWST's spectroscopic data have confirmed these results multiple times. Spectroscopy, which involves breaking down light into its different wavelengths to determine the age and physical properties of astronomical objects, has provided crucial validation. The data revealed that these early galaxies not only existed but also contained elements and a number of stars that are inconsistent with a young universe. While we have made significant strides in understanding the temporal edge of the universe, the spatial edge remains elusive. Searching for spatial boundaries presents a paradox. If we are looking for an edge in a space that exists now, we must see this space in real time. Imagine trying to find the walls of a vast concert hall in the dark, illuminated only by a few distant LED lights. You would need to explore physically, but in the cosmos, such personal exploration is not feasible. Instead, we rely on telescopes to peer further into space, focusing on the brighter areas where the light is visible. However, the universe is expanding, so the walls of space are continually shifting as we observe. This dynamic makes it challenging to pinpoint an edge. Additionally, light takes time to travel across space, meaning we always see the past. For instance, when observing distant galaxies, we are seeing them as they were billions of years ago. As a result, although we have not yet found signs of a spatial limit, we have discovered that the universe's expansion rate is not uniform. This suggests that the cosmos might not be uniformly homogeneous but could have a structure we have yet to fully understand. The JWST's journey into the cosmos challenges us to rethink our search for boundaries and beginnings. The telescope has uncovered structures that defy conventional limits and expectations. One remarkable finding was an extraordinarily active galactic center, with a quasar exhibiting immense luminosity just 570 million years after the Big Bang. This quasar's brilliance, powered by a black hole 10 times the mass of our Sun, sheds light on the dynamic and complex nature of the early universe. In its search for exoplanets, the JWST has demonstrated that we must move beyond the concept of limits. The discovery of exoplanet HIP 65426b, a gas giant 12 times larger than Jupiter, exemplifies this. Located at a distance from its star that is 100 times greater than Earth's distance from the Sun, HIP 65426b was directly imaged for the first time thanks to the JWST's advanced capabilities. This is a rare achievement, as most exoplanets are discovered through indirect methods. The JWST's findings reinforce the idea that the universe is full of phenomena, peculiarities, and dimensions that challenge our understanding. The search for an edge or limit may be misguided, and the universe itself continuously reveals its boundless nature. Neil deGrasse Tyson's observation that the universe is not only bigger than we can imagine, under most scales, it is bigger than we can imagine, underscores the profound mystery and scale of the cosmos. This mystery deepens as we confront fundamental questions about the universe's nature. Does it have an end or a beginning? Can the James Webb Space Telescope, JWST, provide definitive answers to these questions? For millennia, humanity has sought to comprehend the scale and boundaries of the universe. In ancient times, the edge of the known world was thought to lie beyond the horizon. Today, our instruments have expanded our vision, allowing us to observe the universe on a scale previously unimaginable. The JWST represents a leap forward in this quest, aiming to explore the farthest reaches of space and time. This telescope could be pivotal in determining whether the universe has a definitive edge or if its boundaries are beyond our current comprehension. Understanding whether the universe has an edge involves grappling with the nature of cosmic boundaries. Historically, our understanding of edges has evolved. While Earth and our solar system have tangible boundaries, such as the atmosphere and gravitational influence, the universe's edge is a more abstract concept. It could be a literal boundary or a metaphorical threshold leading to other dimensions or realms. This distinction challenges our conventional thinking about limits. Neil deGrasse Tyson's assertion that the problem with the size of the universe is in our heads, and not in the universe itself, highlights a crucial point. Our tools for observing the universe are still relatively primitive compared to the vastness we are exploring. Presently, we can observe approximately 46.5 billion light-years in every direction, resulting in a total observable diameter of around 93 billion light-years. Despite this immense scale, we have yet to identify a definitive edge. The JWST has already made significant contributions to our understanding of the universe. Designed to look further back in time than any previous telescope, it explores the so-called dark ages of the universe, the period after the Big Bang when the first stars and galaxies formed. However, the discoveries made by the JWST have been both surprising and challenging. One of the most intriguing findings is the discovery of 6 galaxies that appear remarkably mature and developed for their age. According to the JWST's observations, these galaxies should not have existed so early in the universe's history. Instead of observing nascent galaxies and protostars, the telescope revealed fully formed galaxies, challenging our previous understanding of cosmic evolution. This raises questions about whether we have correctly identified the universe's temporal edge or if our models of its early stages need revision. The discovery of a massive galaxy cluster existing much earlier than previously thought further complicates our understanding. Traditionally, it was believed that individual stars formed first, followed by star clusters, galaxies, and then galaxy groups. The presence of a galaxy cluster at a time when the universe was still very young suggests that our models of cosmic evolution might be incomplete. The JWST's observations have also shed light on the temporal edge of the universe. Galaxies with a redshift greater than 10, indicating they existed when the universe was only about 2% of its current age, have been detected. These findings imply that the early universe might have resembled its present state more closely than previously assumed. This revelation challenges our understanding of the universe's development over time. Spectroscopy, a technique used by the JWST to analyze light from distant galaxies, has confirmed the age and properties of these early cosmic objects. By breaking down light into its constituent wavelengths, scientists can determine the age, composition, and physical characteristics of astronomical objects. The spectroscopy data revealed that these ancient galaxies contained elements and star populations inconsistent with a young universe, suggesting that our previous models of cosmic evolution need adjustment. The JWST's discovery suggests that our traditional concepts of boundaries and edges may be limiting our understanding of the universe. The telescope has revealed cosmic structures that defy conventional limits, highlighting the need for a new perspective on cosmic exploration. One remarkable discovery by the JWST was an active galactic center, featuring a quasar with a black hole 10 times the mass of our Sun. This quasar, located in a galaxy only about 570 million years after the Big Bang, emits enormous amounts of light due to the friction of material falling into the black hole. This finding illustrates the dynamic and complex nature of the early universe and challenges our understanding of cosmic development. In the search for exoplanets, the JWST has also demonstrated the need to move beyond conventional limits. For example, the direct imaging of exoplanet HIP 65426b, a gas giant 12 times larger than Jupiter, showcases the telescope's advanced capabilities. Located at a distance from its star that is 100 times greater than Earth's distance from the Sun, this discovery highlights the diverse and complex nature of planetary systems. The JWST's observations underscore the idea that the universe is full of phenomena, peculiarities, and dimensions that challenge our understanding. Rather than searching for a definitive edge, we should embrace the boundless nature of the cosmos and remain open to discovering new dimensions and phenomena. The James Webb Space Telescope has profoundly expanded our understanding of the universe, revealing its complexity and boundlessness. As we continue to explore, the JWST's findings challenge traditional notions of cosmic limits, urging us to embrace the universe's infinite nature. Our quest for knowledge is an ever-evolving journey, reshaping our comprehension of the cosmos and our place within it.